just I'll click the right. So yeah, so you're right. It is Chinese, the I Ching, and then the 120 cell is a different sort of research topic. But let's get into the 120. No, sorry, we'll start with the I Ching particles. So there's a bit of background to discuss on this, I guess, but I'll just set this up first. Yes. So I don't really have an awful lot of. I suppose if we use Wikipedia to search up the I Ching, it would be the most kind of expedient way of getting into the topic. So as it says here, it's a system of divination. I'm not sure how far it goes back, but it's obviously quite old. Yes, and well, the principal idea of these things called yarrow sticks, but there's something a bit obscure about that method. Usually they have these things. They usually have 3 coins, and so you throw the coins, and let's say you get all heads, and then the next time you throw the 3 coins, you get all heads. Then that's your first trigram, and that's your second, and together they create all these hexagrams. And there's 64 in total. And then the order that they're placed in, here it's just 1, 2, 3, 4, 5, 6. So they're just, I think they're just in order. No. So the specific order of this, this is the King Wen order, is disputed, like, as to why it is in this order. So there's a man called Terence McKenna. I'm not sure if they speak about him here, but they might do. No, probably not. But I might as well search him up as well. So Terence, I'm not spelling his name right. Yeah. So Terence McKenna was he's an ethnobotanist, and he's a philosopher as well. And then so he created this thing called a time wave zero. And so effectively, it was a computer program that him and his brother made, which was how does it? So that it's based on the mathematics of the I Ching, and then it was supposed to have a time loop that gets progressively faster and terminates in around 2012, right? November, December 2012, and then he tied that to the Mayan calendar. So if I just go back here. So yeah, so we kind of follow in their footsteps a bit and create the trigrams, and then we build them up into hexagrams. Then we have the King Wen sequence. Nobody really knows, as I mentioned, nobody knows where the sequence originates or why it is in this order. So we just place the hexagrams alongside that in the correct order, and then we can sort them. Now, here's the part that McKenna sort of contributed. And basically what it is, so this is the list of hexagrams in the King Wen order. And then we just shift them back by 1 and take the difference. So here, all the 1s are different to this. So the difference is 6. But here, there's 2. So the difference is 2. So these are the differentials between all the hexagrams. This is just how we get them. So 6, 2, 4, 3, 2. And what I noticed is that, oh no, sorry, what McKenna noticed was that there was no number 5 differential in the King Wen sequence. Obviously, we could use a different, we could pick 2 random, not randomly, but select them specifically, and we'll get a difference of 5. But in the King Wen sequence, there's no difference of 5. Now, the question is, well, why is this the case? And one of the things that is related to the I Ching is the magic square 5. So this magic square. And the interesting, so basically how the I Ching first came about was this important person saw he was like an emperor or something. We probably could have picked that up from the Wikipedia article, but basically he saw this turtle climb out of the Yellow River, and on its back, so the turtle had 6 parts to its shell, and there was 1 dot on this part of the shell and 2 here, 3, 4, 5, so like that. So then he realized, oh, so that was the first sort of divine inspiration for a magic square of order 3. Now so there's, go back here, there's 8 trigrams. So these 8 trigrams then correspond to these 8 squares here, and then the 5th one is in the center, and you can create all of the reflections and all the different transformations of this that still all sum to 15, and the number 5 will always remain in the center. So it's like a kind of like a still point or a fixed point in the process. So you think like, oh, the reason why there's no order 5 difference is because 5 plays a crucial role in the whole system, but only by its absence, in a sense, you know. So that's my thinking. But then Rajan had another very good point, which we'll get to, but in more detail. But basically, Rajan, you were talking about how there's this crystal symmetry, isn't it? And you can have, you can have order 2, 3, 4, 6, but not order 5.
It is by group theory. You have the symmetry, 5-fold symmetry. You cannot have 5-fold symmetry. You know,
right? But as you mentioned,
that's
disputed, right?
It's disputed, but it's not exactly what Penrose were talking. It's not exactly that. From a crystal point of view, this is very, very clear. You know, I was one of the few people who were doing in Penn State with somebody. I mean, little bit, like a couple of few months. But the group theory, there's a rotation matrix. You can actually prove there's a complete proof that shows why 5-fold symmetry cannot exist. Now, the crystals, you can have that under certain conditions. You know, the quantum thing is totally different, right? I'm talking about the macroscopic or
I've seen images, though. I've seen images of so this is like a 5-fold symmetry crystalline tiling. But I think I've seen images of you know, well, kind of like what they're saying here. Seems to maybe they're saying there's a 5-fold thing there, maybe here as well. But I've definitely seen images of like micro, what do you call it? Like electron tunneling microscope kind of.
Images exactly. The microsymmetry. That's why microsymmetry is different from macrosymmetry. You know, when I was teaching X-ray diffraction, I kind of pointed out the microsymmetry you probably can have 5-fold symmetry. The macrosymmetry, you cannot have 5-fold symmetry. So the mesoscopic level, you probably don't have 5-fold. But in the quantum level, you have time crystals and all they're talking about, right? The same way, a lot of exotic things happen at the quantum level. So you can create a 5-fold symmetry at the quantum level. So that's what they're talking about. Microsymmetry.
Yeah, I don't know though. So I think it was. I mean, it was small, but I wouldn't say it was. You know, it's not like it was at a quantum level. Like, you know, they were definitely real crystals that were really there. Now I don't have the image. So.
No. You can create from the quantum level.
Yeah,
I have
create from the quantum level, and then you can then observe at the mesoscopic level. But you are creating it. You know, naturally, you cannot have it.
That's right, because a crystal would have some sort of seed.
I have read about electron microscopy. There are 2 modes which are very popular with electron microscopy. The one is called SEM. It creates an image by detecting reflected or knocked out electrons, and the other mode is TEM. uses transmitted electrons that are passing through the sample to create an image. So, and actually, there are pictures of real atoms. They succeeded with, I think, with one of the two electron microscope modes to photograph, to record pictures of real atoms to the Armstrong level size. So this crystalline structure, is recorded by electron microscope. You can see the crystalline structure of what Christopher just shown there in Wikipedia of the atoms.
I like this kind of thing.
Well, this one. This one.
No, I a PhD. I worked on both. SCM is called scanning electron microscope. Electron microscope. Then STM, scanning tunneling. Transmission electron microscope. I worked with all of them.
That's your specialty. That's your specialty. I forgot material science. So you work with tunneling. Fine.
Tunneling later on. I work with the scanning later on.
Okay, if we have a seed particle for this crystal that's going to grow, and it happens to be 5-fold, then it's going to grow and it will have a 5-fold symmetry in the mesoscale and because So I looked at the proof. Well, I looked at a mathematical proof online for the 5-fold and why it doesn't exist. And it was on YouTube, and in the comments they were like, "Oh, this is the best explanation for why this is the case." But I watched the video. It was like a mathematical proof, but it didn't really explain why that was the case. It just had numbers and angles, and so
rotation matrix.
It was more to do with kind of angles and signs and things
geometry.
like that.
The reason is geometry, because there are specific geometrical shapes, these crystalline structures of the atoms. This is very much connected with geometric table with a 5 in the center. It definitely has some connection there, some correlation. The magic table with a geometric structure of these atoms.
Yes, so this was it. This was the interesting part of this. I suppose, like, they seem to be building off some sort of grid structure in the mathematical proof that is very square, and then they say, oh, well, if we take this angle and bend it this way or tilt it, take this angle, rotate it this way, we get, these are the possible angles we get, and 5 is not one of them. But then, as we can see, it does seem like 5 is a possible one. But so I just thought I'd bring that up. Just to go back over the previous work we did last week, then I noticed there was an error. I believe all neutrinos have 0 charge. And one of them here was like 1 or something. So I changed that and redid it. So these are all the charges for the chiral particles, neutrinos, electrons, and quarks.
Christopher, can you enlighten? Because I lost you now here. You're talking about neutrinos. What is this code? Because I'm not here. The last time I was not here, so. Can you fill me up a bit? Elaborate.
Sure.
On this,
So these are So these are just the particles of the standard model. So we have the electron, and then L is just the chiral part. So that's the left-handed one. This is the right-handed one, and then V E is, nu E or whatever is the. Here I'm just representing it with a V, is the neutrino electron. Then we have the quarks, and they're chiral. And so these are just the charges then next to them. So we see that the neutrino has 0 electric charge, whereas the electron supposedly has 1. And then the quarks have this fractional charge, which was very how do you say it, was very controversial, I think, when it initially came out. And then the star here just represents the antiparticle of all of these, the ones that we just discussed. And so you see some of those
Sorry, is this an animation program? Is this code for animating something or calculating parameters? What is the output of the code, of this code?
Oh, well, there's no real code. So this is just a data structure here. This is called a dictionary. So we have the key, which is the name of the particle, and then the value, which is the charge.
You're indexing. It's an indexing program. You're indexing the particles of the standard model.
Yes.
Kind of index. Yeah, with all the parameters they have and all that stuff. The spin, the magnetic moment, chirality, and all that stuff. Oh, okay. I see now. Yeah.
Okay, but in this case, it's just the charges. Now, one thing I've noticed is that I have the anti-electron here with a charge of 1, but I don't think that's right. It needs to be -1.
Yes, an anti-electron is a positron. An anti-electron is actually a positron.
Oh, so there,
charge. Yeah.
So there it should have a positive charge. So this one should be the negative.
Yeah.
Right. Good point. Thanks for that.
Yes.
Yeah, because I'd originally done this in a different program, and then I saved it in a different file, and then during a different sort of implementation I was doing, my computer crashed. No, I wasn't taking proper care, and I lost all those notes. So I kind of had to redo this. And I just did it very quickly. So we might have to run this from the beginning, actually, or else it's all going to fail. So where are we now?
Yeah, that's very impressive, actually. A lot of work. That's very impressive, all these parameters.
Oh, thank you. Yeah, this is what I do all the time. This is why I'm like, yeah, maybe I'll start using an LLM to just do simple stuff like this, but I don't know if it's worth my time yet. Okay, so like we said, with the fractional charges were a bit controversial, because how can you have like a third of a charge or something? So one solution to this was just to simply multiply the charges by 3. So now instead of -1, the electron has -3 charge, and all of the quarks are now integer charges. So that's a nice solution for sure. Now we get into adding the weak isospin. Now I suppose I should preface this then maybe with the fact that, should I? Yeah, so yeah, I should. So well, we spoke about the I Ching. We spoke about Terence McKenna's contribution with the missing fifth differential. And so my thinking was, well, you know, we have the charges for the standard model particles, and then we get the weak isospin and the hypercharge. And one of the facts about the hypercharge is that there is no number 5 hypercharge either. So the idea then was we're kind of relating the King-Wen order of the I Ching to the hypercharges of the standard model particles to see what we can learn from that. And specifically, the question was, oh, wait a second, that's still magic squares. So I don't know if they're going to have the image of it here, but basically, yeah, so it's to recreate this then using the particles of the standard model instead of the hexagrams. So this order, and specifically this 8x8 kind of matrix. Okay, so right, so here's the weak isospins, and again, we're just building up a dictionary. If it's right, if the particle is right-handed, it doesn't matter if it is matter or antimatter. The weak isospin is always 0, and if it is antimatter, the particle will have a weak isospin of -1. Otherwise, it's going to be +0.5. So these are only for the left-handed particles. which is to say that the weak force only interacts with left-handed particles. So it's this chiral symmetry breaking of the CPT violation. So then we build up our data structure with those values for each of the particles, and now we just calculate the hypercharge, which is the charges minus the weak isospin of the respective particle times the number 6, and then we just take the ceiling value of that, and that gives us this as a result. So no number 5, but it does have negatives, and the mirror side of this will have the opposite negative charges. Okay, so I'll just run this again because we made some changes, and it does seem to affect the order of things, which is something that could be studied later on. It's kind of interesting. It seems to have made everything much more streamlined, actually, which is good. Because initially I had there would have been 3 particles here, and it was about 10 or more of these 3 particles, which kind of made it all a bit more ambiguous. And then when I corrected it, I only had 2 in this row. And now that we've done our further corrections, it's streamlined it a lot more, except for up and down. So yeah,
Christopher, a parenthesis here. So if I got it correctly, you have the Chi combinations with the 64 combinations.
Yes.
Actually, and then you have the hypercharge and isospin combinations, and you want to find the correlation between the Chinese Chi particles with the combinations of different combinations of the particles of the standard model, the charge particles, the fermions. Is that right?
Exactly. Yeah.
Yeah.
So that's what we've done here.
If this is true, which is very important, if this is true, then you have to adopt that the standard model and all the particles in nature have a binary logic, because it's 64 is 8 times over 8. It's 64. Yeah.
Well, not exactly, because the I Ching is not a binary. It's not binary in the sense that if you add 1 and 1, you get.
Sorry, do you know the Tower of Hanoi, the other puzzle?
Yes.
The Chinese have, and you have n-1 combinations. So if you have 3 disks, then you have I think you can do 8 different combinations. Yeah.
Right.
And if you have 4. Then you can do I think 5 64 combinations like that. So it's an exponential with a base of 2 function.
Right.
And this is binary logic. You have discrete steps.
This is not binary logic. So because I can see where you're coming from. These are binary numbers in a sense, but when if I take one of these and then a different one, and then I combine them, I just stick them together.
Yeah.
This thing here is no longer any kind of binary number. You get me? Because we don't add them in the way that you would like binary numbers, where 1 + 1 = 0, and then you move the 1 up. So so we're not adding anything here. We just stick them together, concatenate them. Okay. So yeah. So it's yin and yang rather than 1 and 0. If you know what I mean. That's where they're coming from here, I think. Okay, but I mean, there's certainly a binary thing in it, in the sense that it is dual. It's a dualism, but it's not binary logic in the sense of base 2 mathematics. Okay, but everything else you said was spot on. Yeah, we're looking at the hypercharges, and we're trying to match them with the order differentials of the King-Wen sequence. Okay, so now we have this. And so we've achieved that because, wait a second. Yeah, we've achieved that here. So here's the King-Wen order down the left side, and here are the associated particles. And you know, except for this outlier here, all of them are unique. So that's a really good sign. And then this is it in the 8x8 matrix that we were after. So you see this line here looks to be either the same or longer than it was before. Now, I haven't done an awful lot of contemplation on the results to see how interesting they are or what they kind of tell us. It was something that I wish to do, and that one doesn't seem to be too changed. Okay, and that one's going to be the same. So, but this is where it gets more interesting. So this is kind of moving on from the previous work. So we know there are no differentials of 5, and we know that there are no particles with a weak hypercharge, and we know what we seem to be of 5, and we seem to be suggesting that there's no crystal symmetry of 5. But however, that seems to be disputed from this quantum level seed packet up, and we're dealing with the quantum world. So then we ask, well, what if there was a particle with a hypercharge of 5? How would that affect things like mass and so on and so forth? So basically here we start again with the data structure.
Yes, of course, you are right, Christopher, because if you get results that are building up, that can mean only one thing, that the elementary particles are actually composite particles of one of this particle you're seeking with, which has a base of 5.
Yes.
Yeah,
this is a kind of, this whole thing is,
there's a structure actually. There's a structure underneath you study. You have a structure which is building up and giving the next result, the next result, the next result on the table. And there's a fixed, finite quantity, a quanta, that is used for getting the next result, the next result, the next result, the next particle. So that this implies that the elementary particles of the standard model are not elementary, and there is a more fundamental particle behind. In my case, in my studies, this is graviton.
Well, we shouldn't jump ahead too quickly, because I'm just introducing this. But
no, it definitely implies your study implies that there is another more fundamental particle behind.
Yeah, I suppose in the same way that we would have, like, let's say, the Higgs boson, but before the electroweak symmetry breaking, we have 4 Higgs bosons, and again before that happens, we have what is it? You have these 4 electroweak particles that no one knows what they are, and then out of that fall the W boson,
the W and Z boson, the W and Z boson.
Yeah. And then the photon, right? So which is the electron charge carrying particle or force. So
how about Christopher? How about it's a very good point, Emmanuel. Thank you. So Christopher, how about the monopoles? Are there possibilities that arise from here?
Not exactly. So, like I said, we should just what I'm kind of building to is maybe a sort of a leptogenesis, like Emmanuel was suggesting, but also, you know, not a baryogenesis, but like where even the bosons are kind of created. So, however, to do that, we need to postulate this initial particle. So I'm not sure if it's correct to say that everything is. Yeah, no, Emmanuel makes a good point, but we'll see how like all-encompassing that is, or how, you know. Okay, so
Christopher, if the particles, the elementary, were actually the elementary, according to your analysis, you could not do this analysis you're doing right now, because if it's something elementary, it's the bottom. You cannot analyze it more. You cannot find any structure. So the fact that you can analyze and find a correlation between the particles means there's a structure in the background of the particles. that means that these particles are not fundamental. There's something more fundamental behind.
That's right. Yeah, there's a thing that occurs first and then the other. Yes. So I would agree with that. Kind of similar to the symmetry breaking. But we'll see how it actually, operates now.
Sorry,
this is where
things get
pretty weird, So we have the weak iso spins again. These are just the same ones. 0 for the right-handed, minus 1/2 for the anti-left-handed, and 5 for the left-handed. So this is just to print it out in a human readable way. What we get is, once we have a hypercharge of 5, which is absent, and minus, and then we do our calculation, then we wind up with this new particle that hasn't existed prior to this in the standard model. When it's spinning in the right to the right, it has a charge of 1/12, and when it's an antiparticle and spinning to the right, it has a charge of 1 1/3, and you can see the left-handed particle is 1/3. Okay, so as we know, we're supposed to multiply by 3 in order to get rid of the fractional charges, and we have fractional charges here. So we multiply by 3 and we get 4 and we get 1, but we also get 2.5. So we're back to fractional charges. So we don't want that. So in order to get rid of them, we multiply by 12 instead. And that gives a right-handed particle of 10, anti-left is 16, and the right-handed, or the left-handed, is 4. But this is really strange, because we're suggesting then, so let's say we really have 2 particles here. We have which we're going to call this particle the X particle, let's say. We have the anti-X particle.
Question, Christopher, if I may interrupt. You need to only multiply by 2, right? But because 5 is not there, that's why you have to multiply by 4.
No, we multiply by 12 to get rid of all the fractions, because our lowest one.
No, 2.5 times 2 is 5. That's a complete charge. But you say the 5 doesn't exist. That's why multiplying again by another 2. Because you need only.
Yeah, but it's just to pick because they just chose a single number. They just take the charge, multiply by 3. So I said, instead of going, well, multiply by, you're saying you can multiply by 5, but then how would that affect the other part?
2. Multiply by 2, then you get 5, 8, and 2, something like that.
Yeah, but you have to multiply by 3 first, so then it's 3.
Yeah, that's okay. The last one.
6, is it? Yeah. Okay, so that's an interesting point. So, okay, so you're saying we could just do multiply by 6 and get the. Oh yeah. Okay. So there you go. I just thought right. So you can multiply by 6 and then you get these values, which are perfectly valid. Yeah, and then because this is where my maths is possibly not the best. So, and then we could have just multiplied this by 6.
Yeah.
And then we get 5 is what you're thinking. Oh yeah, that's pretty cool actually. Okay. Yeah. We're gonna have to return to that maybe after I've finished.
Okay.
Because we're kind of rewriting the script as we go, which is cool. But I don't know how to we need to reinterpret what we've got. Okay, so right, we've got that, and then we can use the minus hypercharge as well, and we just get the minus values. So the odd thing about this then is that we have a particle that has a different charge depending on whether it is a matter particle or an antimatter particle, or depending on its spin, whether it's going to the right or to the left. So there could be reasons why that is forbidden in quantum mechanics. I don't know what those reasons are. So, ignorance is bliss. So
yes, the closest case I know about a particle that has this erratic behavior is the neutrino. The neutrino has neutrino oscillation. So imagine it like it has this shape, and the next moment it has this shape, and then it has this shape. So it's changing between an electron neutrino to a tau neutrino and to a mu neutrino. So it's imagine like a ball that shrinks and then expands and then shrinks again and so on.
Yeah.
So, but I'm not sure that if I remember correctly, the spin is still 1/2 because it's a fermion. The mass is changing.
Yes.
Because neutrino has mass, the mass is changing. One question only. You are assuming that, according to your study, these X particles, you call it, is it a boson or a fermion?
It appears to be a fermion because it has chirality, and it also has charge.
So it's half spin. It's half spin.
Sorry, it is half spin. Yeah.
But it's changing. You say that it's changing constantly. Is charge? The charge is not the same. It changes depending if it's an anti-X particle or X particle and so on. Right.
Right. So if the particle is moving through space-time and it's changing from its chirality from right to left as it goes, then its charge is going to fluctuate between 10 and 16, or minus 10 and
all right. Okay.
Minus...
Well, that's actually possible. I think neutrinos do that as well. I think.
Well, yeah. So this is the electrode.
I mean, neutrinos don't have charge. Neutrinos don't have charge, but they do that with the mass. The neutrinos don't have charge, but they do that with the mass. During the oscillation from tau and neutrino, they're changing the mass. Yes, theoretically, you could have some kind of particle that is changing its charge. Not it can change also its charge depending if it's right-handed. And actually, when you finish, Christopher, the very interesting presentation. I have to share with you a story.
I'll be back in a few minutes. Thank you.
Yeah, about the gallium anomaly, because anomalies are the best things to do new physics. You know.
Yes.
So I will continue the neutrino because neutrino is a very interesting particle, and I see you picked it also up here to study neutrinos. And there is actually an anomaly. It's called the gallium anomaly, and this anomaly is unresolved for the last 20 years. They cannot explain. I will explain briefly what this anomaly is, and it has to do something with oscillations, again with neutrino oscillations. So yes, but please continue. Don't let me disturb you anymore.
Okay, thanks very much. So there's another interesting fact about what's going on here, because if you notice, there's the particle, there's the antiparticles, and then there's these antiparticles. So there seems to be 6 particles where, so there's the matter particle, there's the antimatter particle, and then there's the anti-antimatter particle in this situation. So that's a bit odd as well. So instead of just, instead of having, let's say, a particle and an antiparticle, we now have 3 particles, and then, well, we have 3 different charges for one particle, and then we have the anti-charges of those, which makes 6, right? So we now have 6 new particles, in a sense. Okay, so now this is all redundant, because instead of multiplying by 12, we should multiply by...
Sorry, because I'm really interested in what you're saying now.
Yes.
So can you give an example? So this particle X has, for example, let's say charge -2, and then it can oscillate to the next to +2 charge, which is the same case as the electron and the positron. It's the same case, actually, the same analogy. But I don't understand this anti-particle, because 2 negatives makes positive. So if it's negative,
I know.
it's again.
I mean, well, my understanding,
perhaps I'm wrong. The charge like that. will be just a positive charge with a different quantity. That's what you mean. So it's not. It's now not 2 minus 2 or 2, but it's plus say no -3, for example. Is that what you mean?
No, no. Actually, don't. No, I like. This is a new kind of thing. So I'm thinking it's more to do with like Boolean logic, where one thing negates the other, but then you have like and or particles. You know.
Yeah, it's binary logic, Boolean logic. Yeah. So if you have you know, a not makes one against the other, then it's gonna end.
Right. You could have like and or you could have and or nor or XNOR or something, and you couple them in a certain way so that they cancel each other out. In kind of like how quaternions work, where you have, you know, I times j equals k, and j times k equals.
So this the third group is just has no charge. So you have
they all have charges. So, but some of them have negative charges, which means they're the anti. These are anti to those, and this is already anti to this one, and this one is anti to that one. And this is also anti to that one and that one. So
because usually if you have a positive charge, it's a right-handed. It has a right-handed chirality, and if it's negative charge, it has a left-handed.
No, that's not correct. Well, that might be the case in neutrinos. They were thinking, but then they discovered that neutrinos have mass, like you mentioned with the oscillations. So then they said, okay, well, there is a possibility then that there are, you know, left-handed left-handed neutrinos and right-handed anti-neutrinos, but it's just the idea that the weak force doesn't bind to right-handed particles.
Yes, neutrinos, actually the only neutrinos they have discovered, they're all left-handed. All other particles have right-handed and left-handed versions.
Right.
But the fermions is the only.
They never discovered the right-handed one, but some people are suggesting
it's the sterile neutrino. It's the hypothesized right-handed neutrino. It's called sterile neutrino because
initially
it has no charge actually.
Well, yeah, they don't carry charge. That's correct. Yeah. Okay, so yeah, I mean. This is the question. So we have this very strange particle, or 6 particles really, and so then after this, so we ask, well, how are these going to interact with each other? Well, so here we have the kind of redundant issue where we've just multiplied all the particles by 12, and we should probably multiply them by 6, as Rajan pointed out. So that is not going to affect it that much, I don't think, but we're going to have to re-step through it with the correct values at some point. Okay, so
Christopher, can it be that this particle X you're looking for is actually something like the neutrino? It's actually oscillating. It's just one particle that changes all the time, and it's similar to a neutrino oscillation. Can it be that it's not 6 particles, just one, and it's oscillate all the time?
Well, I mean, it's a bit like how somebody will say, "Oh, we discovered a new particle, okay, and it's the electron, let's say, okay, but then there's the anti-electron, and that's considered, or like the positron, that's considered a separate particle. So in that case, when you discover one, you automatically discover 2." Yeah. So that's the exact same thing that's going on here. We discovered one particle, but then we found, so if we discovered one fermion, we've discovered 2, yeah, because we have the anti-particle. But now we have the anti of the anti-particle, if you know what I mean. Yeah. So that's 3. And then if we are throwing in the right and the left handedness because of the different charges, if we consider a particle with a different charge to be a different particle, then now we have 6. Because we don't know the masses of these. If they have different masses as well, then that just kind of, well, it doesn't mean anything, because you could probably have 2 particles with the same mass. You can certainly have 0 mass particles. So, okay, so right. So here's just the table. Then we have the right-handed X particle, right-handed or left-handed X particle, the anti-right-handed particle, the anti-left-handed X particle, and then see, I haven't come up with names for these. the star left-handed particle, and then the anti-star left-handed particle. So we notice that there's more left-handed particles than there are right-handed particles. So that's interesting, and that might explain the chiral anomaly that we get. So if these are the particles that are going to bring about leptogenesis, that would explain why more left-handed particles can come into existence than right-handed particles. If left
why there's more matter than antimatter? Why there's more matter than antimatter?
Well, that's what I was initially thinking, but I'm not sure. When you start running the calculations, you kind of see that it's the matter and antimatter seems to be created in pairs anyway. So there's still a symmetry there, although it is believed by physicists that the reason for the, what is that called, the antimatter antimatter asymmetry is exactly that. It is something to do with it should be linked to a chiral anomaly. So if that's the case, then this could be the solution to that problem. But I think the solution probably lies elsewhere, because I can't generate that asymmetry with these particles, but we can generate a chiral anomaly, which is handy. So again, using the incorrect value of this number 12, we find that, you know, a right-handed X particle won't interact with a right-handed other X particle. So anything where the particle is the same, there's just no interaction. Now, but if it's an antiparticle, you're going to get 0. So that's why along the diagonal here, it's going to be all zeros. So these are just the straightforward antiparticles. But if you've got like a right-handed X particle and an anti-left X particle, you're going to get -6 will be the charge, or -12. And since 12 was the charge of the electron, we're suggesting that when these two combine, they create the electron, or no, the positron, and then when these two combine, they create the electron, and then otherwise they create this particle which is kind of half the value of the electron, and that's so 6 or -6. We call this particle 6p. So this is another particle, another new particle, which we suggest can combine again to create an electron. So this could be like electric and magnetic. I'm not sure. So we have the anti. No, we have the anti-anti. No, this is the anti-anti. So, dang, I haven't come up with a name for these yet. I've just been thinking about. I've just been following the notation. So
yeah.
So the star X.
Don't use too much X, because then you will correlate with Elon Musk and X. You know, Twitter X.
Right.
X,
yeah, but
X,
and there's already an X particle anyway, so I shouldn't really be calling them. I suppose we could call them the Wen particle, King-Wen particle, the Wen. How's that? This is better than the I Ching.
Maybe you can call it the O'Neill particle. The O'Neill particle.
No. That's, you're not allowed to name it after yourself. You can name it after. You can name it after. Well, remember, there's now 8 particles, right? So, which is kind of funny, but or is there more than 8? No, there's 8. Okay, so the Wen star particle, the anti-Wen, and the anti-Wen star particle. Okay, so just like we said, if we add these two, we're going to get an electron. Add these two, we're going to get a positron. these will create the new particle and the anti-particle. So this is the kind of algebra needed for this, if you like, or which means that we can add 2 6s together to create this, to create that, which is the positron. But we could reorder this and say, well, this and this cancel out, leaving this and this, which is just what we had originally. So it makes sense that this will, or just what we had originally here, sorry. So it makes sense that this will come out an electron. So that makes sense in a sense. So here's a diagram of this kind of interaction. We have the positron coming in, splitting into the left-handed when and the anti-star when. And then it can also split, as we've seen, into...
Are these, Christopher, are these Feynman diagrams? Are you using,
yes.
Are these Feynman diagrams? Okay, okay.
Yes.
That's good.
Okay, so we also have the second set of antiparticles. So we have the when right-handed and the anti-right-handed. So these are gonna cancel to form, in this case, a photon, and then they're gonna break apart again and come together with this original thing to create the positron again. So we can do this with the normal electron as well. So how this would appear then in like a bubble chamber or something like that would be positron comes in through the left, nothing happens, there's some break, then we see a photon, then a break, and then we see the positron again, or the electron. So that's the signature that we're looking for to say that this is real, I'm guessing. Now, there's another issue, which is that the charge of the left-handed when particle and the anti-left-handed particle is the same as the charge for the down particle. So is there, we could ask, are these functionally the same object? Or would they sit in the same place? So if we have the the star when left-handed particle is the down, then it could decay using the W minus boson into an electron and an anti-neutrino electron and an up quark. So now we're getting, so initially we were getting from these, what was it, 6 seed particles, we get a new particle, then we get the electrons, we get the photon, we get the bosons, the neutrinos, and the quarks. So this is the leptogenesis part I was talking about. And then we can go on from this and create more Feynman diagrams. Here's just one again that splits into this, because we have these weird star, anti-star, and normal matter particles and antimatter particles, we get these strange 4-leaved kind of
I see this inside your capsule there. These are all virtual particles.
Yes,
these are virtual particles.
So
are you assuming that your X particle is a virtual particle?
In a sense, because we have the, I suppose. Well, I think it's just the way you have...
Is it stable? Is it stable? Is the particle stable? No, because you say an electron comes in and then it breaks down to a photon and then comes back again as an electron.
Well, that is that's a possible interaction. This is also another kind of weird possible. Well, actually, let's just focus. So let's say you have a. Yeah, I see what you mean.
Yeah, I mean, don't get me wrong. When I say virtual particle, in my opinion, and not just my opinion, but also even Hawking is talking. Virtual particles are actually real particles, but we cannot observe them directly.
Right. You know? Yes.
It's the stuff that makes all the particles actually. Is this what I call the quantum flux, the quantum form? Everything is made from quantum form. All the particles of the standard model. So virtual particles, because many people say that virtual is not real, it's just a mathematical trick. No, 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 no. They are very real. We cannot just observe them. That's why they call. I can actually point you exactly to the where Hawking's giving Stephen Hawking is giving a lecture, and he says that virtual particles, we call them virtual because we cannot measure them, but they are actually real. Yeah.
Right.
So virtual particle is actually if the elementary particles of the standard model are composites, it will prove the new physics in the next 10, 20 years that they're actually composite. They will be composite made up from virtual particles. That's for sure. They will be made up from virtual particles because virtual particles are what comes out from the vacuum. All this, all this stuff with they get created in a split second, and the next second they get again combined in a particle, matter and antimatter particle, and they get annihilated. And this is going all the time. So I believe that quantum foam is the last secret to the key to uncover everything is the energy of the vacuum. Everything imagine it like every particle is just a manifold, a smoke manifold, a smoke ring, some kind of shape. So the quantum foam is the smoke. It's the vacuum energy, the 0 point vacuum energy. And this is the stuff which made all other particles, bosons, fermions, and that stuff. So if your particle X is a virtual particle, you are just in the right direction. It must be essentially a virtual particle. So don't be afraid to say that it's not a virtual particle. Well, it must be virtual particles. That's actually the Feynman diagram you're showing here.
Right. Well, no, it's not that you see, this is just very new, like stuff. I just came up with this kind of last night, kind of put this all together. So like, I'm doing it very quickly, and in my mind, I was thinking of, the way you'll have a photon comes in here and it splits into an electron and a positron, and then they recombine into a photon or so. I suppose that's a possibility, but it's very unlikely. So I was kind of going with that point of view, but if these, because usually when I think of virtual particles, I think of bosons, so like the W boson or they'd be the kind of virtual particles.
No, they don't call them, actually they are virtual. Come on. They live for 10 minus 23 over 10 seconds. I mean, it's a femtosecond of the femtosecond or something like that. So but they don't, because they're very important for quantum physics, they coined them as not virtual, but real. And they put them in the table of the standard model of particles.
Of course, yeah.
So if you ask a physicist, a particle physicist, they will tell you, no, they're not virtual, they're real. Come on, nobody can see them directly, and they're unstable. Of course, they're virtual particles. Of course. But,
right. Yes. See,
Emmanuel.
Yeah.
If I may interrupt, I have two questions, Emmanuel. One of them is the quasi particles. Are they real quasi particles? When we say quasi particles,
yeah, you missed that. Rajan, you missed. I had just this conversation with Christopher.
Oh, thank you. I had to go.
Yeah, they're real. Yeah. Of course, they're real. Even the Stephen Hawking.
Quasi, even quasi particles.
Stephen Hawking.
I'm sorry, what is a quasi particle?
Yeah, they're real. They're definitely. Stephen Hawking said in one of his lectures that the virtual particles are real particles. We call them virtual just because we cannot directly observe them. That's all.
So are you saying that another term for a virtual particle is quasi-particle?
Yeah, like partons. They call partons.
Oh, yeah.
Partons. Or unparticle.
Oh, you mean
partons.
The quasi. Do you mean like those ones that are kind of, they're emergent particles out of?
Yeah.
Oh yeah. Sorry, yeah.
And the second one is I agree with Manuel about the quantum form, because in my new paper, that I send now, which is published now, quantum gravity thing, that I think you are going through that. I do mention about the quantum form at the 0 point field. Quantum foam has 0-point field.
Virtual particles are actually the 0-point energy vacuum particles. That's
right.
The quantum foam, all this quantum flux, 0-point energy. They're all referring back to the virtual particles.
Superfluid, superfluid. And all that.
But they are distinct, in usually from quasi particles, which are like phonons or something, like something that's generated out of other particles. But who knows? It could be the same thing at the end of the day. So yeah, the worry I had here.
No. Quasi particles is totally different. Quasi particles are not virtual particles.
But maybe you could say like that the virtual particle in the quantum foam is actually a quasi particle within the foam. Do you know what I mean?
Oh yeah, of course.
That's where I was
quasi particles is if you have an electron or a photon in the vacuum, it has some properties. When you put it in a very dense medium, metal, for example, and some kind of alloy, its parameter can change. It can change. It has a refractive index. It can even the fine structure constant can change. There are examples of the fine structure constant when it's in the vacuum is 1/3. The number, and when it's inside the medium, it becomes 1/10.
Oh yeah, I've heard about this. And
yes,
even the fine structure.
Well. So the changing the medium, the interaction with the crystalline structure of the metal of this medium can change the behavior of the photon, and the photon actually can become can have mass. Even if you it can become massive the photon. Like that's called quasi particle. And even an electron can become massless. An electron inside can behave like massless, and the photon can behave as it would be massive.
Oh, that's cool.
Like a boson,
that's exactly the graphene. The graphite, about the graphene properties, there's these strange properties. It's all the particles there are becoming quasi particles, and if it's very thin, micron thin, then the behavior changes, and the electrons become massive, and the photons become massive, and the electron becomes massless. That's why they have so much conductivity.
Okay. Well, Christian was saying that I remember I asked him about that before, about the changing of the. I think it was in relation to the work you did with him with the horn torus, but he was like, because if you go back close enough to the Big Bang with the singularity, I think the the alpha number you're talking about there,
the fine structure constant.
137 or whatever was a different value at the beginning of the universe, and he was like, no, that's not true. Like it never changes; it's always the same. And I was like, yeah, okay, but you seem to have the you think that because I thought that was just theoretical, but you're saying no, this is actually proven.
No. I have the paper. They have experimentally measured the fine structure constant inside the alloy. And it was different. The value 1/137 is for the vacuum.
Okay, yeah. I mean, I have no problem with that.
If you have a medium, if you have a medium different from the vacuum, it's not sure that it will remain 137. There are actually examples of special metal alloys that the fine structure constant is changing very big. There is a very big change in the fine structure constant.
Okay. Okay, let's get back to this then, just to finish up.
Okay, very nice picture, Christopher. Nicely put schematic down. Yeah.
Right. So these are all the new particles, because I think you missed most of this, Rajan.
Yeah.
We've got like eight new particles.
Basically, you said the photons come in and they become positrons. Is that positron electron? Is that what it is?
This is a positron, and it splits into, because the positron in our new configuration has charge 12, but we're going to redo that with your thing where we just so it'll have charge 6 instead. So this will be charge 3, and these will all change. their respective charges. So
that's anti-positron. Is it anti-positron?
No, this is a new particle called when particle. So we have the when star, we have the when left-handed, the anti-when, the
chiral.
and the n right. When that's actually very hard to say. When right-handed, and then we can also have the when anti-star. So this is anti to this, and this is anti to that, and that is anti to this, and this is, you know, so there's like there's three anti-particles. So it's some sort of Boolean logic that we need to work out. So it'd be like NOR and XNOR or something like that. Well, we'll look into that, or maybe it's not a Boolean logic and it's just a total mess. But we'll see. Well, it works anyway. I'll ignore the arrows here. I think it's supposed to go in different directions for anti and minor.
So it flips and then it combines on the right side. It's combining.
Yeah, recombines here back into this. So and in the middle though, so it splits into these four different kinds of matter, antimatter particle, and then rejoins into this new particle, which is half the charge.
Sorry, Christopher. Christopher, sorry, just a question here.
Yeah.
Because I will forget it after. Because electron and positron, positron, but electron is the most stable particle. It has a lifetime of billions of years.
Oh, okay.
Can you apply this also for the electron, or is it just for positron?
Oh yeah, you could do it for the electron as well. Yeah, I just didn't do it. The example I have here is, so for the electron, it's split into this or this group here. Rajan, could you mute your microphone there? There's a bit of crosstalk.
Oh,
if possible. Or I think it's from here.
But why you say that the electron will or the positron? Because they are stable particles actually. If they are not come together as matter antimatter, they will not be destroyed. So is this a case? Why you say that the positron will for some reason break up?
Because no, that's a good question. Yeah, so I think no, that is a good point. So I think that in some sense this is like demonstrative, but then you have a fair point. But like, so it's more about how the electrons are created. Do you know what I mean?
Okay, so it's leptogenesis. Okay, I understand now.
Yes,
you're referring to leptogenesis.
So, right. So then, point, though, because I was also saying that we should be able to observe this signature, but then from your point, this is not possible. So I'm incorrect on that.
I don't know. Maybe.
I think I am. Go ahead.
If you force it, yeah, of course. But under normal conditions, the electron has no reason to break up spontaneously. You know.
That is a very good point.
Yeah, it's very stable.
Yeah. No, yeah, you make a good point there. Also, just to go back to the earlier point, which was also very good that you made. So the reason why I was a bit hesitant to answer your question was because when I think of virtual particles, I think of them as bosons. But earlier I pointed out that these are obviously fermions, right? Because they're chiral. So then we'd have so essentially we're talking about a virtual fermion, which is
yes, of course. You
cool?
It's cool. It's okay because you have electron and positron pairs all the time coming out of the vacuum, and then in the next moment they will combine and annihilate. So these are fermions actually. They're virtual. You can have virtual bosons. You can have also virtual fermions as well. Yeah, of course.
Okay. Yeah. So maybe So maybe it's some kind of, like you're saying, out of the 0 point energy. This is maybe some possible cycle that's creating virtual particles.
You're describing the process inside the quantum form now. Yeah, I understand.
So this is fun. So leptogenesis, as we say, to create
one more thing is how does it compare to the quark? You know, these are all made of quarks, right? So can you explain in terms of the quarks?
Yeah, that's an interesting question that we covered, because if we look at the charge of the left-handed particle or the left-handed star particle. It's 4, right? So that's the same charge as the down quark. So at one point I was suggesting that this particle then could stand in for this, and we could have an interaction with the W minus boson to create electrons and anti-neutrinos, or and then the up quark. So then we have like a full kind of leptogenesis where we're creating photons, W bosons, quarks, and then out of that gluons, obviously, and neutrinos. So the only thing that we're not reaching is the graviton. Yeah. So, and then out of those particles that we already have, we could generate the other 3 families. So I think you could say that this engine here drives like all the generation of all the particles, but it has to be this weird thing that
That's interesting. That's interesting. Yeah.
Hypercharge of 5. Yeah. So if we take this current out of the center here, we could postulate a different current in a straight line, maybe with a 6p particle turning into this engine of or like, how would you say, sort of cross anti-particle when particles destroying each other and going back and forth. But yeah, anyway, this is all just kind of speculation for the fun of it. But we can also kind of try and disprove some of these ideas, because, well, we don't need to discuss that. But let's say we had like a positron coming in, splitting as it did in the previous one, and then we have 6p and 6p, and then they combine back into this. But then we have this double particle that's not anti. So if we went this way, we're not creating an anti-particle and a matter particle. We're creating 2 matter particles in this case. And then if we switch it up where we have a matter and an antimatter 6p particle, then when they combine, we find that we have this is doubled here. So either way, we have these duplicates, which would suggest that these are not valid Feynman processes. So, that's just a basic rundown of the situation up until now. So I think we should maybe go back and just change the 12 value to 6.
Christopher, just a moment. Can you just scroll down to the Feynman diagrams with the leptogenesis? The leptogenesis Feynman diagrams. Can you? Yeah.
This one?
Here. Stop here. Yeah, this one. Why, if it's leptogenesis, if you describe leptogenesis,
right?
Why you need the lefty positron there?
Why do we?
Yeah.
Why do we need left and right?
Yeah. Why you need the left positron? Just scrap it out. So you have your 2 X particles that combine and they make a positron. That's it. You're referring to leptogenesis, right? So.
True.
You don't need to have the left electron here. The left positron.
Oh, that's true. Yeah. Good point.
If it's leptogenesis, you in the beginning you don't have the lepton. You have only the X particles coming out of the foam and making of the quantum form of the vacuum and making up the positron. That's all.
That's a reasonable statement. Yeah. Okay, so yeah, I can make those changes. And in the meantime, I'll make this change first. So what do we say? We're going to change this to 6. This is just a duplicate of the other one, but I might as well change it anyway. So we're basically changing to 6. 6. 6. So this, there's an 8, which is going to be, I don't know what this value is going to be. It's going to be like 4 maybe. Oh, and all of these will need to be changed as well. Okay, so let's just run this first. So we get 5, 8, and 2. And then, okay, so, right, so it's just half. And then this was, so the electron now is -6. The up is 4, down is -2. Okay, so that's fine. We go 5, 8, 2. So 2 is the same as the down, which was what we had before, so that's fine. Do we have any other? We don't. And we have now a particle with a charge 5, which is cool. So 2. Let's see what happens here. It'll probably be an error. Oh no, that didn't work out. Okay, so we got lots of 3s and 6s instead. And then this will be the same. All of that needs to be changed. So it's basically 3s and 6 rather than 6s and 12s, which is fine. So, okay, so it's not a huge difference, but it's going to be, just means maybe to correct what we've already done, so to make sure that works out. So I don't know what you want to do. Do you want to take a break, or where still there?
Yeah. 10 to 15 minutes probably we can take a break then.
Okay, cool.
I'm actually fine. I'm actually fine. I don't need a break. So make it 5 minutes. 10 minutes is too much. 5 minutes is okay. 5 minutes break.
Okay, 5 minutes.
Okay.
Because I have to go with my wife in half an hour. I will go for out. It's Saturday night.
Well,
so I cannot stay more than half an hour.
Okay, that's fine. Well, even I can get back. The other part of this research is totally separate. So it's based on do you remember all the work I was doing with the 24 cell and the 600 cell? I don't know if you were here for all of that, but basically I was doing a lot of the stuff where it was, where we have the U1 and SU2 and SU3 symmetry groups, and then the idea was the grand unified field theory, or grand unified theory, that just combines those all into a larger group structure. So SU5, glass shell, and those.
Coach theory, yeah. If it's a coach theory with SU2 and SU1, the theory of everything must have just one, combines everything in one. Yeah, that's true.
Right. So that was the aim, and obviously Garrett Lisi also did one using the E8 Lie group. So I was just following on from the research done by other people into string theory who were using, I think it was, the 24 cell for bosonic string theory and 24 dimensions with the Weyl group, Weyl vector, and all of that. So I did that, and then I expanded. So I got all the particles in the standard model, mapped them to the 24 cell and its dual, and then expanded that to the 600 cell. So then I was able to include, what was it, quantum chromodynamics. I was calling it electroweak symmetry breaking, but I'm actually wrong about that. I should have been calling it charge parity, or the parity breaking, so the chiral thing that we're talking about here most of the day. It handles that very well through a process called the S8 matrices, which are very similar to the order 3 magic squares. In fact, some of them are order 3 magic squares, about 8 of them are. So then it also, U1 is in there, obviously. SU2 is in there, multiple copies of that through SL2Z and 2Z. And then, so it's definitely a grand unified theory, but then it's how to take that 600 cell and create a theory of everything. So we want to include
gravity. You have to combine also gravity. So it's grand because you combine the electroweak with quantum chromodynamics and the electromagnetism, the classical. But that's a grand. That's not a theory of everything. Theory of everything, you have to put also the graviton inside. That's the difficult part.
So this is the next step then, to take the 600 cell.
But
so
I'm very impressed. Christopher, I'm very impressed. You did in the meanwhile a lot of work. That's a lot of work.
Yeah. Well,
and it's very mathematical, and Bravo! Yeah, I'm really impressed. Yeah, that's fine. So
Thank you.
I can give you actually an exercise so you can verify your theory, or even try to verify the theories.
Cool. Experiments.
I don't know. It's called the gallium anomaly. It's
Oh yeah, you mentioned it.
I will finish first, and how much will you take to finish? Because I can mostly wait another 40 minutes. No, that's all. 40 minutes.
Well, hold on.
I have to
Yeah,
go.
right. So, well, we take a break then, and when we come back, you'll explain the gallium anomaly.
No, you can finish your presentation first, and then.
Oh right. Oh no.
Yeah.
Oh, that's fair. Yeah, no. I finished the I Ching presentation.
Okay.
And then we said we take a short break before moving on to the 120 cell.
Okay.
Section.
Okay.
And then
so
you mentioned you had something to talk about to do with the gallium anomaly. So
yes,
I don't know
if
you want to speak about that when we get back.
Okay. So, should we speak after the break? 5 minutes break.
Sure.
Yeah.
Okay.
I just want to mention. Probably you already know the the Gell-Mann and all, how the octet structure came into being. The octet structure came to being from octet is for the strong field is from Buddhist eightfold way. You know that. Anyway, we'll talk after the break. We'll come back after the break.
And the Eightfold Way is part of the I Ching, isn't it? Or it's part of Buddhism.
Buddhism, and that's what the strong theory, the Gell-Mann, thing is based on that. The color charge and based on that octet, the eightfold way.
They're all connected, yeah.
And then so we have a new thing here, which is a new set of 8 particles. And because I've been looking for, the way in the 600, or no, it was the 24 cell model, we had all of the fermions in there and all of the bosons. It was 8 vertices that had no particles. So it would be interesting if these 8 new particles are those particles, because previously we were called dark matter.
Okay.
That'd be pretty awesome.
Yeah.
So let's take the break 5 minutes, guys. Right?
Great. Thank you.
Thank you.
Hi.
Oh.
Yeah, just a small presentation of this problem. Where's Rajan?
Yeah, we're just waiting on Rajan to get back. But
can you hear me?
I can hear you.
No.
Rajan's not here. Yeah. Okay. Oh,
can you hear me? Yeah, I forgot my earplugs.
Okay.
I couldn't hear. So is Rajan here?
Not yet. I don't know if you want to start. We can.
Yeah, I mean, I think we'll wait for Rajan. Or is he? Did he leave?
No, he'll be back. He's just.
Okay, let's wait for Rajan.
Okay. In the meantime, I have to probably open a few tabs on the just to explain the next course.
Okay. I can present anytime if you want, right? I can present. Yeah. Okay.
On the gallium issue or the yeah, I probably should open this one as well.
So is it how's the weather in your place? Is it hot? Hot?
No, it's been really nice today. It was sunny, but there was a real I don't know, it was almost like an autumn day or something, or yeah.
Here in my city is 37 degrees. 37 degrees. Under shadow. Yeah, under shadow. It's very hot.
Yes.
I'm actually here under air conditioning. I have 3 air conditioners. I have all 3 open now in the lab. Yeah.
And has your summer been very hot in general?
Very hot. Yeah. 37 degrees. 37.
Yeah, that
Celsius,
is hot.
Celsius.
That's
Celsius.
like Arizona almost. Arizona, we have, and in Fahrenheit, we'd say Fahrenheit 100
yeah,
and
it's 37 plus 38 to make the conversion to Fahrenheit.
You have to do just 9 over 5 plus 32. So multiply by 9, divide by 5, then add 32. Yeah. So if I do that, you get 763 plus. It's about 100 plus. Yeah, I think. Yeah. 100 Fahrenheit. If you do the calculation, let's. Oh.
Wait, so is 100 Fahrenheit, which is around what, 32 or something?
It's 98.6 Fahrenheit.
Yeah.
98.6 Fahrenheit. Yeah.
Yeah, I did a mental calculation very close. Yeah.
Yeah, it's times 9 divided by 5.
5.
You
then
take
add
the
32.
Celsius, multiply it by 9, and then divide it by 5 to make it the conversion from Celsius to Fahrenheit. Yeah.
And then add 32. After 9 over 5.
And then add 32, yes.
32.
And then, And then add 32, all that.
So 98. Yeah, that's good.
Yeah.
I remember.
So let's, because my time is limited now.
Go ahead.
Yeah, the gallium. Actually, I was not aware about this anomaly. It's an anomaly which is it's persisting the physics community almost 20 years now. The gallium anomaly. And what is the gallium anomaly? So, Rajan, you have to mute your microphone.
Yeah, I muted him. All right. Yeah. Just crosstalk. Okay. Go ahead there.
So what is the gallium anomaly? So what I have to present. Yeah, I forgot that I have to present. But before I present, let's make it more now with graphics. Yeah, with live graphics. So they have a sample of gallium, right?
Okay.
And the sample can be a ball, 1 kilo ball, a square gallium. This material with the strange properties. They're shielded with lead, 30 centimeter lead, so they make sure that nothing can pass, only neutrinos. Yeah? And of course, they do the experiment below the underground, maybe 30 meters underground. They're shielded with lead. This sample of the target sample of gallium, and that so they are now sure that it's not bombarded by muons, cosmic rays, gamma rays, but only neutrinos can pass through the shielding and then target the gallium, right?
Mm-hmm.
So then there's actually a reaction when electron neutrino hits gallium, a gallium atom. It knocks out an electron, and if the gallium is a heavy gallium isotope, 71, it can transform to a germanium 71. So if gallium is bombarded by neutrinos, it can spontaneously transform from gallium 71 to germanium 71. So, and it gains the germanium, I believe, knocks down one. So it's the one has an atomic number. I believe it's 32, the gallium, and the germanium is 31, one electron less, because it transforms the gallium atom to germanium via beta negative decay. The beta is electrons. Beta radiation is electrons actually, and negative means it loses, it emits, and the gallium emits an electron from his shell and becomes and transforms to a proton. It gains the neutron becomes a proton, and that therefore it becomes germanium, which is more heavier. I think it has one atom, one proton more. So the germanium 71 has 33 protons, and the gallium 71 has 32 protons. So what's now the strange thing? They do the calculations, and they discover, if in that case of the gallium, that they have production 20% less, about 20% less of germanium atoms. So they were expecting more gallium atoms to turn into germanium, but have a deficiency of 20 to 24%. And this was confirmed by 3 separate independent labs through the years. The last was at the year 2022, and they cannot explain this. This is a known anomaly, but it cannot be explained. Why you have this 20% deficiency in the conversion of gallium atoms to germanium. So there was a paper this year, I think beginning of January. I can send you the links. And there's now a new theory about what you have to explain this, the phenomenology. So you can, why it's a good exercise, because if you have a new theory, you can use the phenomenology of your theory and see if you can explain something unexplained. So this is a good check to check with your theory. Maybe you can explain it. You explain this unsolved mystery, the gallium anomaly. So let me present you now for I can present, I believe. Present.
Sure.
Share screen. Yeah. Screen sharing works for best. Yeah. Share screen. No, entire screen. Entire screen. Share.
Did you click on the win? You know the way you can see your screen there in the inset. If you just click on that and then click on share.
Oh, yeah. Yeah.
Oh, there we go. I think that's it.
Yeah.
Well, okay. It's loading. I don't see anything yet. It's kind of.
Yeah.
I don't. No, we don't see it.
Yeah.
There we go. Soviet American gallium experiment.
Okay. The gallium anomaly. Yeah, you can see.
Yeah, Baxan.
The gallium anomaly.
Oh yeah. Oh, this looks interesting. All right.
It's a description from Wikipedia. The gallium anomaly. Can you see this text?
Yeah. Okay, so in June 2022, so it's quite recent. The best experiment.
Yeah.
Cool.
Yeah. Released
so
two
it's
papers.
20 to 24
deficit. Deficit. Yeah, deficiency. Yeah. So I have put so this here is the reaction. You get the gallium atoms, but it must have been a heavy isotope of gallium. Otherwise, you don't see this anomaly. So you have a heavy isotope of gallium atoms, and they react with electron neutrinos. That's here, this part here, and spit out an electron and germanium. So it turns actually this electron then reacts with a neutron and turns to the proton, and the gallium atom gains one proton, and therefore it becomes a germanium. That's the most detailed reaction.
Mm-hmm.
Yeah.
Okay.
So
interesting. Yeah, this is very.
I have put in the physics. Yeah, I have put in physics tax exchange. I have put a question about it because I also want to explain this anomaly. I try to explain it as well. So, yeah.
And how far have you gotten? Do you think you're close to explaining it, or?
No.
I like your avatar.
Yeah, of course.
Yeah.
It's my electron, my spinner. Yeah.
So you're asking, can the gallium experiment be explained by the anomaly?
Okay. I will present you now the question in physics tax. Actually, physics tax exchange is a very good place to discuss and learn things.
Okay.
And because you discuss with experts there. And, yeah.
So they're very good.
So here is the and I'm asking here if it can be explained, because now what is the theory of this new paper, the 2024 paper? It's actually a review paper. It's here. So what it's saying, we know that the neutrino is oscillating all the time. It's called neutrino. Neutrino then can change to a tau, and then can change back to the electron neutrino. Yeah, so you know.
Yes.
But
you're breaking up a bit. You're cutting in and out a bit there, Emmanuel.
Let's wait the screen to update.
Okay. Yeah.
We can't hear you very well, Manuel. We can't hear you.
I don't know if it would help to close some tabs. No, you don't have that many tabs open. Maybe.
Why? No, you don't see my screen. I will stop and then try again.
Okay.
Present.
Yeah, we lost the last maybe 10, 20 seconds of you speaking.
Okay, share screen. Share screen. Share. You say share screen, yeah, and then you told me I should click not the entire screen, just a window.
It's up to you. Yeah, window could work as well.
But I want to the entire screen.
Okay, well then go. Yeah, click on entire screen, and then there you go. And then
I think that's much better. So.
Cool.
So this is the latest article from 2024, It's published here in this part, in this Science Direct, Elsevier actually, this journal, and it's a review article. So it's reviewing all we know up to now about the gallium anomaly, and there's now a new explanation, possible explanation why this is happening, and the explanation is it goes as this. Because you have the neutrino, which is all the time oscillating between its different phases, mu neutrino, tau neutrino, and so on. You can have maybe they're speculating, they're assuming that maybe because all these three neutrino oscillations are left-handed, but they say that some of the time it can oscillate between and become a right-handed neutrino, which is so far not been observed. A right-handed neutrino is called also a sterile neutrino. You know sterile? You cannot have kids. Yeah. So that the sterile neutrino is not will not react with the gallium atoms. So that's why, therefore, you have this deficiency, this of 20% less. So yeah, that's the explanation, but they cannot prove it yet. It's very difficult to. They do experiments all the time, but they have not proven it. But if it's true, that will be the first indirect confirmation of a right-handed neutrino, which is actually a dark matter candidate, because this neutrino, the right-handed, will be much more massive than the left-handed neutrino. So if they discover that, the right-handed neutrino, which is sterile, it does not react. It does not react with a gallium atom. That will be probably an explanation. So you have this neutrino, which is all the time changing shape. So it becomes tau neutrino, mu neutrino, and some of the time, 20% of the time, say, for example, it becomes sterile. It becomes a right-handed neutrino, and that's why you have less 20% less germanium production. That's now we can say the prevailing explanation, but it's still unproven. So you have here. Okay, let's see the reactions. So this is the first reaction here. Can you see? It's 71 gallium. It combines with it gets bombarded by. Let's make it larger. Yeah. So this here is an electron neutrino, and the gallium here it gets bombarded by this neutrino, and then the gallium releases an electron from the and becomes germanium. You see, because it's through negative beta decay. If the gallium loses an electron, okay, this here is the best reaction. You have the electron neutrino. It bombards a neutron of the gallium atom, and then it releases an electron, and the neutron becomes a proton. So now the gallium gains one more proton, the gallium, and becomes germanium, because germanium. This is combined the number of neutrons and this number here, 71, is combined the number of neutrons and protons. So the gallium becomes 31, has 31 protons, and the germanium gains one proton and has now 32 protons and one less neutron. So the gallium gets transformed to germanium. That's all. And this is because now the electron, the electron neutrino, because it's only the electron neutrino can do this reaction here. If the electron is a muon electron, not a muon electron, not a neutrino electron. A neutrino, only the neutrino electron reacts and gives this reaction here, and can transform gallium to germanium. If it's a muon neutrino, it does not react. If it's a tau neutrino, it does not make the transformation. And if it's a sterile neutrino, it also does not react. So if 20% of the time the electron neutrino becomes a sterile neutrino, right-handed, that's why this deficiency of 20% less as the predicted.
But why not just say then 20% of the time it becomes either a tau or a muon neutrino?
Yeah, they take this all in consideration. Then it's just another one. You don't have three phases now. You need also a fourth phase.
So they feel like there's not enough. Let's say
there are not enough neutrinos. There are not enough electron neutrinos. The calculation show that they should have 20% more germanium atoms. After,
I know that.
Say, 1 hour of,
what they're really saying then is, if they're saying, let's say this 20%. Now, I was just suggesting that that could all be taken up by tau neutrinos and muon neutrinos, but you're saying
they've done the calculations. They've done the calculations up to the third decimal. They calculate everything. They took everything into account.
Right.
The theory is very, very precise.
So the anomaly really then is that there's not enough tau. Excuse me.
There is not enough electron neutrinos.
No. There's not enough tau and muons neutrinos to account for the non-interactions. So how would they justify it?
No, because they calculated all the number of neutrinos per second of tau, of muon, and these are known quantities.
Oh,
but
okay.
For some reason, they get 20% less germanium production here. This one, because so actually I have tried here to explain it with another process. This process. So you have here. So here are all the possible reactions. If you have an electron neutrino, it reacts with a neutron from the gallium. It releases from the gallium an electron, and the neutron turns into a proton, and this is the reaction we are interested in. This one is responsible for transforming the gallium to germanium. Yeah. All the other here you see it can make a positron. We are not interested for this. Yeah. The muon neutrino reacts with a neutron but does not produce
an electron.
An electron. It produces an anti-muon. So on all that stuff. Yeah. And right. I see now that no, you can turn here the neutron to proton, but remember the gallium is shielded very heavily, so they make sure that no muons are passing. Only the neutrino can pass. Yeah. So anyway, that's the theory. That's the theory that they were expecting 20% more germanium atoms. They don't get it. But there's actually another process here, and that's why I did the question. It's called neutrino electron swap. It's the Wolfenstein-Matter effect. A neutrino passing through matter can interact with an electron bound to the matter atom and transform into an electron, while the original electron becomes a neutrino. So this is actually a swap. So that's another process. Because I have tried to explain, maybe I say the neutrino spontaneously transforms, if it's very energetic, to an electron directly. So in that case, you will not have a contribution to the transformation of gallium to germanium, because it's a negative beta decay. So it's the gallium transforms to germanium by releasing an electron. So however, by this process, you gain an electron, so it will not contribute. So my thought was maybe the neutrinos spontaneously transform to electrons, because this is actually possible. This is possible via this process here, and also via this process, the Wolfenstein matter effect. So if a neutrino is passing very close from an atom, it can spontaneously transform to an electron. And when this happens, the electron which was bound in the atom becomes a neutrino. So you have an electron that flies by. Let me stop sharing. So you have the atom here, and then you have the neutrino that is flying by very close to the atom, to the gallium atom. Because it's passing, if it's very energetic, one of the bound electrons of the gallium can turn into a neutrino, and the electron which passed by, the neutrino which passed by, become an electron. So it's a swap. The bound atom, the bound electron inside the atom, which was interacting with a free neutrino, becomes a neutrino, and the free electron which was flying above the atom, the free neutrino becomes an electron. So it's a swap actually. So you don't gain anything. You don't gain actually anything. But what if this transformation, the flying by neutrino, which becomes the bound electron which becomes a neutrino, is not an electron neutrino, but it's a tau neutrino or a mu neutrino. Then it does not interact. It does not contribute towards the transformation of gallium to germanium. That's my. So I try to explain through this second process, the Wolfenstein effect. Maybe that's why the deficiency. And then this guy came. He seems an expert, and told that no, because this is very rare. This kind of Wolfenstein, the neutrino must be very much energetic, and to become to cause this Wolfenstein effect. So then this guy told me, no, the answer actually the physics stack exchange. His answer was that's not possible,
because it's
very rare. Yeah.
In the text on the Wolfenstein effect or whatever, it said that it was very rare, and it only happens inside stars. So that's going to be my question.
You can have from the sun. You can have some neutrinos who are very energetic, but they're not enough to explain this phenomenon. It's too much. It's 20%.
Right.
So they tried the last 20 years to explain it, and if you read, actually, I will send you now because I forget it. I will send you both now to Rajan and also you.
Oh, thank you.
To have it as a reference, and maybe you can try your model, your theory. Maybe you'll find an explanation.
Yeah. So another thing in the new paper, right, which the quantum gravity, there's another paper after that, but the one I put in the research guide, you all got that copy, right?
Yes,
in that one, I mentioned about how the gravity and this thing, gravity and the time works. So the same way, there are two processes. One is called coupling. The other one is called interaction. Now we put it together, but actually they can have. So you can have a coupling without interaction, which means they just pass by. They don't change anything. But so it may be happening like that. It may be coupling, but it's not interacting. So whereas the other one, the neutrino, the electron neutrino, that is not only coupling but also interacting. So which means that only that portion is active. The other portion is inactive.
Yeah, I mean
not interacting.
One hypothesis is that this tau oscillation, this neutrino oscillation, some of the time becomes a right-handed oscillation and becomes a sterile neutrino, which is a dark matter candidate.
Yeah, that is a good
but
point.
the sterile neutrino will not interact with a gallium atom at all. But
it's like the dark
until
matter.
now, they don't have observed these sterile neutrinos.
Yeah.
All neutrinos
Very similar to
all neutrinos are left-handed.
Yeah.
No,
Very
right.
similar to dark matter. Dark matter, same thing happened. Which very similar thing happened, right? Dark matter also.
Yeah, dark matter also does not interact. That's why the sterile neutrino is a dark matter candidate, because it seems they're not interacting. It has no charge, but it has not even weak. It has nothing.
See, very interesting.
I think that's it.
Charge. Oh no, it doesn't even have weak charge. Yeah. So that's interesting. Yeah, that comes back to another point I think I made last week about
you need to have a left-handed to interact together. Right-handed does not interact with the left-handed.
Right. Yeah. Yeah. Depending on whether it's matter or antimatter, but I don't think.
Yeah.
So then with the dark matter, I think there's a couple of different candidates for dark matter, isn't there? There's this concept of a bosonic dark matter, because for a long time they thought it would be fermionic, I think, and so they had weakly interactive massive particles.
You have the heavy dark matter, but now they are going more to the light dark matter.
Yes.
So that matter that has very light mass. Actually, the first the heavy
WIMP, right? First one is called WIMP. Weakly interacting massive particle. WIMP.
Yeah,
weakly interacting massive.
They haven't found any candidates for the WIMPs. So
that now, they moved on. There are more prevailing theories that there might be these dark matter candidates might be very light, actually.
Yeah.
Talking about axions and dark
the neutrinos are very light as well, so but they're fermionic though.
Of course, I have my explanation in my latest paper. Explains all this stuff.
Graviton, right? Graviton, right?
Yeah.
Oh, that's interesting. I didn't realize. I kind of scanned through it and I thought it was very interesting.
No, I have to tell the explanation of what can possibly be the mechanism of dark matter. It's not. It's actually a particle that can be at rest, but is also massless. You can have gravity. You can have gravity without mass.
Okay, yeah, interesting.
Aka black holes. Singularity has no mass. It's nothing.
Oh,
so why you have gravity?
Yeah,
you can have bending of space-time without having a mass. It's wrong saying that you have exclusive only gravity when you have mass. You can have in space-time. You can have gravity, localized gravity, like a black hole, without having a mass. So imagine that dark matter is some kind of massless gravitational source. It's producing gravity, but without having mass. It's wrong to say it's not dark matter. It's not dark matter. It has no mass. But everything this is in my presentation of my new paper.
Oh yeah, that will be great. We'll discuss more on that. Yeah.
Looking forward to that.
Because I'm very practical. Yeah, I'm very organic. When I say something, if it's strong, it's like a ring. It's like a ring. I really mean it.
Oh,
it's like a smoke ring. Yeah, I really mean it. So the quantum space-time, if it's made from a small, if it's bosonic, if the graviton, imagine the graviton like a smoke ring, but the diameter is 10 minus 77, 10 minus 42, the Planck length.
Okay, but if it's a ring,
minus 42, the radius, So it's a sub-Planck.
Isn't there this concept within the graviton? I think it's from general relativity, and it appears in string theory as well, that the graviton.
Yeah. But they don't say it's superluminal. They don't say that it's superluminal.
Okay, but do you have it as a spin 2 particle? So if you have a circle, that would be U1 technically. I don't know if this really matters from the perspective of your theory, but so how does spin 2
rotation implies automatically, I have proof that spin 2 rotation mathematically now implies directly that it's superluminal. You cannot have spin 2 without having superluminal rotation.
Oh, okay. So
by definition, it must, if it's spin 2, must be superluminal.
I know, but you rotate the. This is my understanding of it. You rotate your graviton by. Well, it says if you rotate it by 180 this way, then the ring is the same. But normally they think about it as rotating it around some axis, like, and it's supposed to come back to itself after 180 degrees, right?
The proof is at in my article, section 2.4. Section 2.4 is the. Let's make it sure. You can read that where I prove that spin 2 is a superluminal rotation. You can read it in section.
But like if you take the graviton, is there some element of it that when you rotate it by 180, it becomes symmetric again?
Yeah, exactly. Yeah, exactly. That's
okay.
Inside the. Yeah, it's
a circle. Well, a circle like
if you go to section 2.4, page 8. Section.
Okay, but you know the question. The question I'm asking is spin 2.
But I have to go now, guys. It's 9 o'clock. I have to go.
Okay, thanks a million, Emmanuel, and thanks for all your help. Great questions, suggestions.
Yeah.
And not to mention,
I believe in my presentation, we can have in my presentation of my paper, we can discuss that more analytically.
Yes, good idea.
Okay, so I
hope to see you next week. Thank you.
I don't know if
have
next week, Rajan, but
whenever,
this month, this month.
Okay. No. Next week, I am just giving the history of physics. I am presenting. If you are come, that will be great. We can just attend. Now I will give the history of physics.
I'm not sure because
okay, it's fine.
I'm not sure, Rajan, because in August we always weekend we leave, we go outside, So
well, this is it. I'm going to be on holidays as well, but
maybe you should
bring my computer or I'll bring my phone. Because you can always just connect. I can connect through my phone and I'll be able to listen to it.
Christopher, if you go in vacation, Forget it. Vacation means you don't have to all this stuff. Forget it. You are on vacation. True. That's all. So
I'll just present it and then later on we can discuss it next week.
Maybe I don't know I'm not sure if I want to present it my paper August. Maybe I wait for up to September.
Okay, August. September.
Yeah, because I'm actually continuing my vacations now.
Fair enough. Also, if Emery stops by or lets us know, then for the especially for the Grail presentation, if he's going to do that.
Yeah, I mean, if I'm up to present, I want to all the members to participate, not just us three. We have an audience of 5-6 people. That would be great.
Yeah, that would. Yeah,
I wait up to September because now August is it's a vacation month. You cannot find people. So maybe
I not seen Gerd for a while. Yeah. Christian was there last week. I think but Gerd was not there. 2 weeks ago, I think Christian was there, but then Gerd was not there for a long time now.
Yeah.
Yes, it's true. Actually, I haven't seen it.
Rajan, for your presentation, maybe you should shift it. I don't know, by the end of August or September.
Yeah, I thought the history of physics.
I'm not sure if everyone will be available next week, because next week we are planning to go for a trip, outside the city.
Yeah. In Greece? In Greece? You will be in Greece or out?
In Greece.
Oh, that's great. Yeah.
Okay.
Yeah, what I can do.
Bye-bye.
Yeah. Okay.
Great time.
Yeah.
Bye-bye.
Thank you. Thank you, Emmanuel. We'll see you. Have a nice day. Yeah. See, one thing I can do is that I can give the presentation, then we can, just even if I'm just myself or you are watching it, and then we can discuss it later so that we don't lose time, because somebody else yeah. So we can, catch, we can utilize the time. So I'll be a monologue that time kind of, but, so I like half an hour, 1 hour. And then if you are able to interact that time somehow, that's good. Otherwise, later on, we can catch up also. So you can watch the thing. So that way we get extra time for Emmanuel to present, Emery to present, you to present, So I don't want to, if I postpone it, then because I want to do the episode 6 next month. Every month, 1 day, I want to do the episode. So it keeps moving till episode 8, end of the year, to the end of the November or something. Then I'll assess, see how things are, and then based on the episode 9 and 10 will go. And then, like I said last time, then I have something written for even documentary movie fight. I mean, we'll discuss that, but 5 to 10 minutes, some interesting video game type thing. I mean, something I came up with. Then in that one, we'll highlight each of them. And so I will draft that and I'll send it to you other people next month, probably like March, April of 2025. And then based on that, we can come up with a couple of hours.
Yeah,
March, 2.5 hours.
March 2025. That'll be a busy time for me though. But
are you defending? Are you completing your PhD?
Yeah. The
maybe later. April, probably after your April, May, maybe. Yeah.
Take a look at it then.
We will see. We'll play by the time, by the year, by the particular time. Yeah, that sounds good. Okay. So it was a great presentation, Christopher. It's very interesting, and then we'll continue again later. I'm saying we are going to pick up that later on because all these are coming together. And then my thing, I finished one now. You probably saw that published. The next one is in the peer review, and then once it's done, it's the next level. Like I talk about Lagrangian and all that thing. This one proves about Schwarzschild metric kind of thing, and the general relativity connects with that. Then the other one connects to the classical Lagrangian, and I give a problem solving for that. And based on that, I might, once that comes up, I'm thinking about it. Then I see how that connects to space and everything. And then at that time, we'll be working together, the project, with connecting the time tensor to the space, the space thing that we are working on.
Yeah, no, so it'll be interesting because I do have some of the research there today on that I was planning to present on the 120 cell.
Yeah.
Like I've gotten to the point where I just plotted the 120 cell and with the 5 different 600 cells embedded in it, and then try to map the particles to the vertices. But there's more work to be done on that, and then there's another stage and another stage and another stage, and then at that point though, it's not clear whether that can be reached, but probably some assemblage of it, like something similar to it, could be reached, and from that we can make certain inferences. But it looks like there'd be, so you have it. So it begins as a 4-dimensional object, the 120 cell, but really the 120 cell is like a dodecahedron in 3 dimensions, but it has these 4 coordinate components anyway. So then the idea is you expand that into hyperbolic space, but it's going to be 4-dimensional hyperbolic space, but it's going to look the same as 3-dimensional hyperbolic space. And then you collapse that down into a grid pattern, which also looks like 3-dimensional space because it's just cubes, loads of cubes in a grid. But it will actually be 4-dimensional, which is kind of weird. But the point I'm making is that those cubes have 3 axes, like, you know, X, Y, and Z. But then those axes are connected by the other axes of the cube. So there's like, anyway, it's a bit hard to describe, but there's basically there's the other axes of the cube, or, you know, the other lines of the cube that make up the dodecahedron when it's transformed are basically time. So then you have three dimensions of time, but that's just time, you know, but it's time on each axis, kind of. But technically it would be 12. Is that right? I think it's, yeah, 12 time axes, but they all conform. They are the same as the original three-dimensional axes, plus this fourth dimension that we don't, spatial dimension, that's kind of there but not visible in some sense. It's like just doesn't it, because everything is four-dimensional projected to three, but then we just, if you don't rotate in that fourth dimension, probably because you're already rotating in it, that you can't see the fourth dimension. So it's pretty cool. But then from that, so there is like, I'm just drawing that comparison between this work and your own kind of thing. But it seems like even though you have these maybe 12 axes of time or 3, it is all just somehow one, you know, because it acts on the axes of the spatial dimensions that we already have. So I don't think that will be a direct link to your work, but I think there's definitely a possibility, because we'd be getting into, I think last week I may have mentioned that I was trying to create a theory of everything using the 120 cell, but thinking about it further, it may only be, you know, like it will take the, let's say, the electroweak and the strong force, so the electromagnetic, the weak force, and the strong force, and then combine that with like special relativity. So not quite gravity, but there is gravity's in there, and it sort of unites with some parts of it. So it's weird. Like, it's not a full, you know, it's not like relativity. I don't think general relativity and this is like fully unified or anything, but there's some sort of connection. And then of course, with all your research and your knowledge of those partial differential equations and tensors, you know, you might be able to figure like some way of maybe you know, how do you say, formalizing what I'm talking about in terms of that language, that kind of notation, which would be handy. But also, but like I said, there's a lot of work to be done in terms of how to transform the hemidodecahedron, which is really just the 120 cell, into the hyperbolic space. And then, so we might have to do that in a simpler way, but a lot of the work is all this complex, you know, upper half plane of the complex numbers. And really, like you were saying about looking into the different elements of lattice QCD and whatnot, the math gets very complicated, and I would like to keep it simple for as long as possible. But really, it seems like this is a very niche area of mathematics, and it's only been kind of explored by, well, it's been explored by a lot of people, but always in the same very highly technical mathematical way. So I don't think there's going to be, I don't think they didn't factor in anyone like me, just like an ordinary person without that very technical mathematical background to maybe have an interest in it, or not that, you know, to actually be using it. So I guess they've not bothered to reduce it in a way that makes it more accessible. So that's going to be a problem, and would obviously hinder any sort of, you know, mathematical transfer from their notation to general relativity. So that's just something to consider.
Oh yeah. So one thing is that what you mentioned about time is that the umbrella model tells that although it's rank 6 tensor, you can reduce to rank 1. So there'll be only one, So the umbrella closes, it is just rank 1. And then opens, it's rank 6. So rank 1 is vector, There's a time just becomes a vector, rank 6. So that's because of wave function. So that is the one. The other one is the partial thing about Levi-Civita, the Kronecker Levi-Civita, that I showed, because space means it in the time doesn't talk about other things. Everything is converted to time. So we don't talk about energy separately or momentum separately, angular moment separately. But when you talk about space, everything becomes into play. So I had to convert. I showed you you had to convert to Levi-Civita symbol, and then your space thing automatically comes there because it becomes the rank 2 or rank 4, and then your space thing, the 4 axis XYZ or something comes into picture. So I convert mine into a Levi-Civita symbol, and yours then corresponds with that, and then the space makes sense. The space comes in that regime.
Well,
and
yeah,
then but the Levi-Civita
it would be a long way off to make any certain connection.
It may not be very easy.
If you're trying to unify maybe quantum mechanics and general relativity, one of the big issues, I mean, there's actually a lot of contradictions between those two systems, but aren't always mentioned. But one of the big one is the fact that you smoothly differentiate over the warped space time. But then when we get down to the quantum level, everything is kind of bumpy.
Continue.
So I'm looking into that, and based on what I can see, it almost seems like the two things would have to be separate. There would have to be, like, to borrow from yourself and Emery's work and the language you're using there, that it would be like a discontinuum between the two worlds. And really been thinking about it last night. It was very interesting to apply some of Emery's concepts, because it would seem like you have this mathematical Platonic world, then you'd have like sort of the space-time universe. That's a different world, kind of, and then the quantum thing happening would be a different world. So you have to have them as like different worlds, but they're just separate, simply like separate concepts, all existing one on top of the other. And so it's fun, but definitely I won't go into any detail then on the 100 cell today. I think we'll just leave it at that.
Okay.
It was quite taxing enough to do I wasn't thinking that we'd have
Emmanuel had a lot of inputs.
Oh, that was great. I'm really glad, and your inputs as well were just both things were really
thank you.
So but also it's kind of cool because I didn't prepare anything for the 100. Well, other than the work that I did do on it for the last week, but I haven't set up any. It'd be better to probably make some notes and have some images, just so I can talk through the concepts a bit easier and a bit more fluidly, because it's not that simple, but it's also So we might as well leave it there, and we will reconvene next week. I might either listen in or you present your thing anyway, and be interested to listen to it. And
sounds good.
Back then, 2 weeks or
a nice week, a nice vacation. Where